Hello to everybody of the Interactive Adaptive Learning Workshop. My name is Alexandre, and today I will tell you about the sample noise impact on active learning. This work has been co-written with my manager, Dreyfus-Schmidt. We both work at Dataiku, which is a software editor for a data science solution, and we work on active learning in this context. First, let's do a quick reminder about active learning. Active learning is a process aiming at making labeling of the data more efficient. So when you have a lot of unlabeled data, it will select the samples so that the accuracy of the model is maximized. So it works in a loop. We gather the data, then we select some sample to be sent to a labeler. Once they are labeled, we learn a model on them. And we use this model to select the new batch of sample until the model is good enough to be shipped. Let's build an intuition in 2D with this simple problem with two classes, circles and cross. You see here the gray unlabeled data, and we have labeled randomly some points. We see the decision boundary of the model in pink. The main method in active learning consists in selecting the samples with greatest uncertainty, so the one closest to the boundary. So we select them, we send them to label. We have a new model, second iteration, and we select samples again, and we keep going until we converge or we exhaust the budget. In this final position, we see that some samples are misclassified, and that's what we call noisy sample that we want to study today. We want to know, are those samples detrimental to the active learning process? Just reset our mind experiment and try again while removing those samples. We keep going and optimize, and we see that we reach the same position in 3 iterations only. So how can we characterize the sample? First, those samples exist in real life. Northcutt has shown it in 2021. They even exist in test set of famous data sets. You see here Caltech 256 and ImageNet. They can be due to errors in the labeling. You can see here the teapot that is not correctly labeled, or to multi-label cases. For example, this image of a frying pan with an egg. Which one should we label? More importantly, they've shown that there are 5% approximately of errors in the test set of ImageNet, and fixing them actually change the ranking of method of the performance on this data set. That's why we believe they are very important. Let's define them more precisely. We've already worked on that in a previous paper where we call them how to classify samples. And we devised a metric that we call reverse accuracy to characterize them. It consists in starting with an independent label set, what you see at the top right, and training a classifier on this independent label set. I remind you, it's a research metric, so it's something we want to have in a research context. It's not something we have in a live experiment. Once we have this classifier, so a classifier that is learned on a lot of data, actually good enough to be considered a good classifier, we use it in our experiment to measure how much noisy sample there are in the batches of our active learning method. And that's what we call the reverse batch accuracy. We've measured that on several experiments, and we've observed that the samplers that select a lot of noisy sample tend to have bad performances. We believe that's because those noisy samples are detrimental to the model. On the opposite, we've observed that some methods, unsupervised mainly, that select really few noisy samples, tend to have bad performance also. And we believe that's because they tend to classify very easy to classify samples, so few information, but in the whole batch, it's not only about those samples close to the boundary. And in general, we've seen that diversity samplers that impose diversity tend to avoid problem due to noisy sample by exploring the sample space. So just by spreading the area on which they select the samples, they will tend to avoid noisy sample. What do we want to do now? So we had this metric that worked on sets of sample and used binary signals, misclassification or not. We want to refine that and to have continuous values, such as what you can see on the right here, which comes from just scikit-learn example. The decision boundary can be a gradient that can be really wide in some cases. We want to use these continuous values, and we want to see if we can integrate them in a sampling strategy. Let's go further in characterizing those noisy samples, so we have this classifier that is good enough that we will call H infinity. The infinity stands for, it's actually in the position of the active learning iteration where we put it. And we mean that it's a classifier that we would get after an infinity number of active learning iterations, so after labeling of the data. And we want to use this value, so the predicted probability for the class of the sample, the true class. Actually, this is something that really goes in the spirit close to the uncertainty score that set up as the most simple active learning technique. One could ask, but do we have such values in real data sets, or do we have predicted probabilities that are all close to 1? We've measured that on several common tasks, CIFAR and fashion, for example. And you see that there are really, most values are really high, but we still have values that are in MNIST, for example, close to 0.3. So on fashion and MNIST, we will expect a low impact, but still something. And on difficult tasks, such as CIFAR 100 or LDPA, LDPA is a tabular data set of accelerometer value, where the classification is what is happening to the people with the device. And it's typically used to detect when old people fall on the ground. For these two data sets, we see that the values are really spread out. So we expect a big impact of this by taking into account noisy samples. Let's go a bit further. So we have this lowest confidence score that has been defined by Settles that consists in 1 minus the maximum value of predicted probability across all classes at a given active learning iteration. So that's really the most basic active learning method. And we wonder, what is this 1 really? So we take the samples that have the highest value for the score. And what is here the 1? The score is basically the information that we expect the sample to bring to the model. So basically, by doing that, we expect each sample to reach a predicted probability of 1 at the end of the experiment. So this 1 really symbolize the maximum predicted probability. But we know it's not the case. The real limit toward the infinity is not always 1. It's what we've defined before, this H infinity. So we have first tried to integrate this value in something we call informed lowest confidence sampling. So it's just lowest confidence sampling, but instead of being optimistic and having this target of predicted probability of 1, we use a real value. Again, this is an oracle that we use in a research setting. So for now, this value cannot be used in a real-life experiment. We then wondered, can we modify a sampler we know to take into account those noisy samples? For that, we started from a sampler we use a lot that is called WK-means for weighted K-means, proposed by Zdanov in 2019. And that works as follows. We have a set of enabled samples. We first perform the usual uncertainty score computation that gives us this gradient of values. Then we pre-select the top values, so beta times the batch size that we are aiming at. And then we run a clustering method, K-means, with a number of clusters equal to the batch size we want to select. And then we take the samples that are the closest to the centroid of the clusters. So we have a mix of uncertainty and the K-means that is here to impose diversity. The problem of this method and all uncertainty-based method is that if we are in a case where we have a blob, an area in the sample space with noisy samples, so here you see a big blob of samples composed of the two classes that cannot be separated. Those blobs will act as honeypot, and all uncertainty method will select samples there, whereas it brings no information to the model. So what we want to do is to avoid doing that by repelling our selection, the strategy from these areas. And that's why we created the incremental K-means. Let's see a bit how the incremental K-means work. So you know that the K-means objective consists in putting the centroid in order to maximize the similarity with the existing points. So here the centroids are the batch and the points are the unlabeled one. Incremental K-means consists in adding to this algorithm the knowledge of the previously selected samples. So not only we will have this centroid that will be the batch, but we will try to minimize the similarity between the batch and the labeled samples. So we want to have the centroids pushed away from samples that have already been selected. And we will be doing that by adding fake centroids, so fixed clusters in the experiment. Let me show you that on the example on the right. So you have this example that we've already seen before with two clear blobs and one noisy. And we have selected a sample in the middle of the noisy blob. What K-means does has no knowledge of what's happening, what has been selected. It just ran clustering, and we have these three clusters. So we will pick, again, a sample in the noisy blob. What incremental K-means does is that at the beginning, it will define a cluster around the sample that has already been selected and perform the K-means on the rest. So we will have three samples selected in the rest of the data, and we avoid the noisy area. That's how it works. We've run it on a simple 2D example. I'm sorry, it's a bit complicated because we had to make it to add a lot of data to see something. But it's basically an example where you have single class blobs here and noisy blobs there. We run 2 iterations of lowest confidence sampling, WK-means, IWK-means, and we observe that uncertainty-based method, the pure one, tend to ignore the single class blobs and focus on noisy blobs. Here, 3 samples selected in this noisy blob. Same for WK-means, several samples selected in noisy blobs and some single class blobs that have been ignored. On the other hand, the IWK-means has spread its selection much better. We want now to see if it translates in real experiments. So we still have one synthetic data that acts more as a sanity check for IWK-means. It's the same disposition of blobs, but there are much more data, much more blobs. So it has been built to have, it's basically an ideal case for IWK-means. That's why it performed best. We also have added a method called K-center greedy. I won't go into the detail, but it's part of a method state-of-the-art that is called core sets and has been designed for CNN. We were surprised to see that actually it works pretty well on this synthetic experiment, as good as IWK-means. And first surprise was that high confidence performed pretty bad. It's actually the worst one. Here is just above random. So we see in the values that high confidence has a very low noisy sample ratio here. So it really selects few noisy sample, but the performance is very bad. So we join again the case that we've seen in our previous paper that some methods tend not to select noisy sample, but then are doomed to select very easy ones. So we could not really conclude on that, but IWK-means is performing better than all the other ones. Now on the real tasks, we've put the table with all the results, but I will only highlight some of them. First, we see that there is no significant difference between WK-means and IWK-means. They have really similar performances on all data sets and similar reverse batch accuracy. So same number of noisy sample ratio, noisy sample selected. High confidence has the highest RVA, so it still selects a few noisy sample, and it has the best score on all tasks almost, except LDPA, where it's one of the worst. So that's something under investigation. But it really surprised us, in particular on Cypher 100, it has very good performances. And the second best, so the best one that could be used in real life are still WK-means, IWK-means. On MNIST and fashion MNIST, one thing we observe is that IWK-means and WK-means are better than high confidence at the beginning. And then they are below, but that's promising for this method because we believe that we can make them maybe as good as high confidence. Remember that we said that in fashion MNIST, there may not be a big impact because there were not so many for high confidence, not so many values that were not one. And actually, there is a big impact. It's a really significant uplift on this data set. And one observation that we're expected is that K-center greedy is not really good outside of CNN methods. So for MNIST and fashion MNIST, we use MLP, so not CNN. And on this task, it performed really bad, which comforts us in the choice of WK means that perform pretty well on all tasks. Now, speaking of future work, for the informed confidence, obviously, it's not something we can use in real life, but it provides a ground truth for active learning. We've never seen somebody researching the best, having a ground truth on a big data set. It could do that and, for example, provide best values for some metrics. We want to explore a bit more by creating informed variants of other samplers like margin or entropy. We also introduced in our previous paper a metric called kappa, that is a proxy that could be used in real life, a proxy on reverse bias accuracy. We'd like to use this and try to see if we can reproduce informed confidence in real experiment, and also try other metrics that are in the same spirit, like the trust score of Giant proposed in 2018. For IWK means, unfortunately, it's not better than WK means, but we won't give up. We haven't shown that here, but we've tried several variants, and in particular, only repelling from a noisy sample, it doesn't give better result. So we hope that in the future, if we can characterize those points better, we could manage to make it significantly better than WK means. Thanks for your attention. I will now answer your question.